Good evening, everyone. Welcome to our reading session for reinforcement learning from Genesis AI Labs. And in this session, we'll be covering the paper titled as Curiosity Driven Exploration by Self-supervised Prediction. So, let me give an overview about the paper. The paper proposes an algorithm, you can say a type of regularizing step that is named as ICM, Intrinsic Curiosity Model. And this paper does an pretty well job in uh, making an algorithm which is able to generalize and learn from the pixel based environments with having sparse or very sparse reward systems. Like in the real life settings, the agent cannot be able to learn due to the sparse reward systems for the environments, but the ICM module has done a very well job in making the agent learn that settings. So they formulated curiosity as the error in the agent's ability to predict the consequences of its own action in a visual feature space learned by the inverse dynamic model. So what that does is evaluated the environments in three different settings. First is the sparse extrinsic rewards. Extrinsic rewards refers to the rewards that are returned by the environment when an agent took an action and moves to the next state. So where the curiosity allows for far fewer interactions with the environment to reach a goal. Second setting is that exploration with no extrinsic reward. So basically the environment doesn't reward the agent to take a step, and the extrinsic reward is actually the zero for the agent to learn. And that pushes the agent to explore more efficiently when used by a curiosity model. The third setting is generalization to the unseen scenarios. Now what it does is gives the agent ability to use the earlier experiences or the learned policy, which was the behavior policy, from one environment and make it able to generalize over a second environment without even learning from scratch. So that makes exploration and the exploitation dilemma much efficient and learned in a faster way. So I have written the bulletin points for the introduction for the paper. Now what they have addressed is these settings that I have discussed right now. The issue they are addressing is that often rewards are extremely sparse. So what does that mean? Is when an agent stochastically, or you can say randomly initialized by a policy in an environment, the actions taken by an agent doesn't actually reward the agent that much. So what it does, it tries to explore as much state space as it able to, and what it does, that the agent somewhat diverges from the goal. So let us suppose the environment is actually giving very sparse rewards, or you can say agent taking a step from st plus 1 to st, let's say st plus 10, and it doesn't actually get a reward for that. So it is very demotivating for the agent to learn a policy in that way. So they introduced a curiosity model which helps in discovering novel states by encouraging effective exploration. Now, how the curiosity can be modeled is there are two ways. First one is exploring novel states and uh, making the agent traverse the state space more. And the second is that curiosity guides the agent to minimize the prediction error of its own action. Let us suppose the agent takes an action at time t and state st. So the agent has to predict its own action on the basis of how good or bad the action would be on that state. So so that is called the intrinsic motivation, and what it does is it is a way to learn new skills which might come in handy for pursuing rewards in the future. So that is the main goal for the ICM model to the agent. Now there are several ways that ICM model can be modeled as. First one is measuring the novelty. How can we measure the novelty of a state? Is like building a stochastic model of the entire state space. Let us suppose we have a very simple environment. Now we can actually deploy a Q learning or a very basic DQN to model the entire state space, because it is actually very less or computationally feasible for us to do so. And but in higher dimensional spaces like the pixel environments or the agent, where the agent learns from visual inputs, that is actually not feasible. Second technique would be building a complete model of the environment dynamics, like how the physics of the environment works, what type of actions and what type of state transitions would be happening if an agent starts to learn randomly. Now, building that environment dynamics would be very difficult for us to, do so in high dimensional spaces. So that approach will be not feasible for us. Second issue is lies between the stochasticity of the environment. Now, the reason for that is sometimes, or in most of the real time or real life environments, the environment consists of noises. It can be distributional noise from the Gaussian, or you can say white noises, where they acts as a distractor, or you can say occlusion objects. So the agent has to learn a policy with inputs that has noise in it. The inputs have distractor objects. Suppose we have a fish environment. Let us suppose we are making a fish one move through the space and let us say achieve a goal G. Now what it does, the visual inputs, let us say we are deploying a CNN to incorporate these feature spaces from the environment. But what happens if a fish 2 is able to occlude over, or you can say overlap on our agent, then it would be very irrelevant for our agent to learn the goal. Like there are several settings where the distraction objects, or you can say many of the noises, are making the agent learn, not learning, but make the agent diverge along reaching the goal. So that will not be, able to learn a better policy on that environment. So one proposed solution to that is reward the agent when it encounters states that are hard to predict but are learnable. So to deal with the stochasticity of the environment, we are actually making an agent which is able to encounter states that are hard to predict but can be learnable via mapping function. So however, estimating the learnability is non-trivial solution as it is. Now the main insight or the key insight for the paper is we only predict those changes in the environment that could be possibly due to the actions of our agent or affect the agent, and actually ignore the rest. So ignoring the rest will be including in like some of the noise that is incorporated in our inputs, and the agent just simply disregards the noise and learn in a better way. So instead of making prediction in raw sensory space, like directly mapping the image pixel features to our agent and making it learn from that way, we are actually using transform, or you can say we map our input from the pixels to a feature space where the information relevant to our actions will be present only. So rest of the noise will be disregarded, and our feature space will be only having such features that actually affect the learning of the agent. So in that way, we'll be able to achieve optimal policy over a duration of time. So that can be achieved by training a neural network on a proxy inverse dynamic task of predicting the agent action given in current state and the next state. Now, as I have described here, since the neural network is the only required to predict the action, it has no incentive to represent within its feature embedding space and the feature variation in the environment does not affect the agent itself. So it's just saying that disregarding everything that is not relevant to the agent's learning and making our learning easier. So we then use this feature space to train a forward dynamic model that predict our feature representation of the next state. So I'll make it easier for you to understand that prediction error of the forward model serves as the intrinsic reward signal for the agent. So what is the prediction error? The agent actually tries to predict the estimate for the action that it is going to take on that state. Like we have at at state st, and our agent is defined as follows. Now what it does, the intrinsic reward model tells us how good an estimate of this action is, and it is denoted by a hat. We'll be looking forward in the next section of the paper. So it is called the forward dynamic model, and what it does is predict the feature representation of the next state. So in the first step, we have predicted the action, and in the second step, using a forward dynamic model, we will be predicting the feature representation of the next state. So this acts as a curiosity for the agent, like accumulating all these steps, we'll be giving this internal reward to the agent to learn in a better way. So the question arises, what curiosity does help in? Curiosity helps the agent to acquire a new knowledge. Like this is our main goal. Our primary goal is to traverse the state space as much as we can, but we cannot actually do that in higher dimensional spaces that efficiently. So what we are doing is giving it a curiosity model, which encourages the exploration effectively and learn skills that will be help acting the agent better in the future interactions. So that is our main goal. Now what they have done is somewhat creating a baseline for the model. There is an algorithm named as A3C, which is a synchronous advantage actor critique. I guess you are familiar with the actor critique methods, but if not, I'll tell you how they work. So actor critique networks works in a way that actor and the critique are two simple neural networks, and the action is taken by the actor, which updates our policy, and that outputs the probability of the actions that will be taken by the agent, and those probabilities will have an evaluation by a critique network. So the critique network tells you that if you are taking that action on that state, how good it will be. So we have an actor, we have a critique, and critique actually criticizes the actions that will be taken by the agent. So it works like a generative adversarial network, like discriminator and the generator. They work in that way. And the advantage actually is the subtraction of the Q function and the value function. Q value function and the value function. What it does is Q value for that state is ATST, denoted by the QSA, and VS is actually the average reward, or you can say average value of that state. So taking a difference on that, the advantage function tells you how good or bad an action AT is on the current state ST. It's that simple. The asynchronous parts actually works on the parallelization of the environment, or you can say parallelization of the agent. Suppose we have 6 agents learning on the same environment parallelly, but the network weights or the actor critique network are shared between them. So let's not go deep inside the A3C modules or how the algorithm works. Let's move forward. So the question that actually makes the paper lean in the way that how good the policy it is able to learn is whether the learned policy, or you can say the learned exploratory behavior, is specific to the physical space that the agent is itself trained on. Suppose the agent is trained on one game, that is, they have experimented on 2 different environments. One is the VizDoom, that is the Doom's environment, and second is this game, which is Super Mario. So there arises a question like how well the agent will be able to generalize itself on different levels, or you can say different environment scenarios. So they have shown that the exploration policy learned in the first level of that game, Mario, helps the agent explore subsequent level faster. So if an agent learns, or you can say perform good and learning a optimal policy in the level 1 of Mario, so that is shown to have good performance when the agent is set to learn the level 2. So the agent, using the curiosity model, able to learn from the experiences that are collected from the level 1, and they are being transferred, or you can say generalizing the experiences well for the level 2 learning. So what is curiosity driven exploration? So the agent is actually composed of the two subsystems. One is a reward generator that outputs a curiosity driven intrinsic reward signal, and second is a policy that outputs a sequence of action that minimizes that reward signal. Sorry, maximizes that reward signal. And in addition to that, the agent optionally may also receive some extrinsic rewards, but in most of the scenarios, the extrinsic rewards happen to be zero, or you can say the environment doesn't reward the agent for making any action. So if an environment doesn't reward an agent to take an action, we create a synthetic reward for the agent to learn from. As you can see, the settings will be different when the environment changes, but most of the environments have sparse rewards, so that ICM makes up for that. And supposedly the policy is always trained to maximize the sum of intrinsic and the extrinsic reward, where obviously extrinsic reward is actually mostly times zero. That is the architecture for how the ICM module works, and agent learns a good policy in any environment. So let us dive into the working of the algorithm. So they have initialized, let us say randomly initialize a policy pi on state st, which is a neural network parameterized by theta p. Given a state st, it executes the action at taken from the above policy. So that is nothing but our behavioral policy, like how an agent initialize a random policy and tries to learn by bootstrapping and any other method. So moving forward, the action is being sampled from this policy, as you can see described as here. Now it is the objective for the policy is to maximize the reward. So that is actually a greedy approach that will be refined in next section of the paper. So what they have overcome is the contribution in this designing an intrinsic reward signal based on the prediction error of the agent. Prediction error of the agent's knowledge about its environment that scales to a higher dimensional continuous space like images by bypassing the hard problem of predicting pixels. So what they does is predicting the actions or predicting anything like estimate for a policy, estimate for a reward, estimate for a state in directly from a pixel space is actually very difficult. So what they have done is transformed, or you can say mapped to a simpler feature space that will be discussed in the next section of the paper. So they have described that making prediction in a raw sensory space is undesirable because it is very hard to predict pixels directly, but also because it is unclear if predicting pixels is even the right objective to optimize. Now, the underlying problem is that the agent is actually unaware of the some part of the state space. Simply cannot be modeled that if the state space is very high dimensional, then we cannot actually model the environment in such a way, and thus the agent can fall into a artificial curiosity trap and stall its exploration. So that is actually seen in the Q learning, which obviously says the Q learning suffers from the same issue as well. So we use the curiosity, which is actually prediction error that environment the agent makes. So how we can deal with that problem? As we can see that uh, currently there is no known computationally feasible mechanism for measuring such learning progress or making such predictions on those high dimensional spaces. So what they have done is divided the sources of the agent's observation into three cases. First one is that things that cannot be controlled by the agent. And the first thing is that things that can be controlled by the agent, like its own action and the transition probabilities that it can make. Second one is the things that agent cannot control, but they can affect the agent. They have given the example like vehicle driven by the another agent. And the third thing is that are out of control, for the agent, and not that will be not affecting the agent in any way. So like example, moving leaves, and you can say if a pixel based environment having the flow of air that affects the moving leaves, so that will be relevant for our agent to learn from. So what they have done, they have described that a good feature space for the curiosity should be modeled from the first and the second point, and that will not be affected by the third one. So if there is a source of variation in inconsequential for the agent, then the agent has no incentive to know about it. Like agent doesn't have to know about the things that cannot be controlled, or and they cannot affect the agent in any way. So coming to the learning part, like how the algorithm works and how a feature space that can facilitate a quality prediction. This is done in such a way that learned a feature space having consists of two modules. The first one is we have states from the environment as S. The first module encodes the states into a feature vector. Let us suppose phi S. The second module predicts the action, giving the feature vector of phi st and the next feature representation of the state. So that is phi st plus 1. And these two are given to a mapping function that can predict the estimate of our actual action that agent will be taken in the environment. So as I've written here, the interactions are performed using the current policy pi s, which is already defined. You can say a random policy has been initialized in the first place. And defining loss over that predicted error of the action is minimizing that loss of predicted action and the original action that will be taken by the agent. So that is happen to be the loss will happen to be maximum likelihood if the action space is discrete. The function is defined as follows. At hat is the function g given the st and st plus 1 parameterized by a parameter theta I. So that is known as the inverse model that we use for the creation of the intrinsic rewards. So that is called the inverse dynamic model. Now moving forward to the forward dynamic model. So our forward dynamic model, what it does, it takes the input AT and the feature representation of the current state and then predicts the feature representation of the next state. So what will be our feature representation for the next state? Will be phi st plus 1, and the forward dynamic model will have to predict the feature representation of the next state. So that will be denoted as phi hat of st plus 1. Now how it does, it uses a mapping function f that takes input feature representation of our current state and our current action. Now point to be noted that current action is not estimate of our action, it is actually the original action that will be taken by the agent in the environment. and that neural network will be parameterized by the parameter theta f. So the loss function to minimize that prediction will be L2 norm of that, and the intrinsic reward signal defined is as follows. Now eta here is a scaling factor, and the reward signal is defined as the L2 norm of predicted feature representation of the next state and the original feature representation of the next state. So that's how the agent is able to get the intrinsic reward from. RTI denotes the intrinsic reward at time t. So basically this is our ICM model, consists of two modules. One is the inverse dynamic model and second is the forward dynamic model. One actually predicts, or you can say estimates, the action value, and the forward dynamic model predicts the, or you can say estimates the feature representation of the next state. Using both of them at the same time results in our ICM model. Now the intrinsic reward tells us how good the prediction of the next state or the feature representation is. So if a reward for the prediction is higher, then the intrinsic reward tells us that prediction of the next state is good and agent is able to learn a optimal policy due to that. So the inverse model learns a feature space that encodes information relevant for predicting the agent's action, and forward model makes prediction in the feature space. So these two modules are being used parallelly in the ICM, and that's how an agent able to learn the optimal policy. Coming to how the loss is being optimized cumulatively. So as they have stated that there is no incentive for this feature space to encode any environmental features that are not influenced by the agent action. So suppose there are few entities in the environment that are not affected by the whatever action the agent takes. So they cannot be used as a reward model for the agent to learn from. So our agent will receive no rewards for reaching environmental states that are inherently unpredictable. So if a state is actually unpredictable, the agent won't be able to go to that state and receive any reward for that. So its exploration strategy will be robust to the presence of distractor objects. Now this paper claims that the distractor objects or the occlusion changes in the illumination doesn't affect the agent learning in any way, but we'll move forward to the graphs and how the learning process experiment takes. That has a different picture to that. Now the use of inverse model has been investigated to learn features for recognition tasks. These are some related papers to that. However, they use the forward model as a regularizer for training in the inverse model features, while they make use of error in forward model prediction as the curiosity reward for the agent are training our agent's policy. Now, optimizing the overall loss function for this method is defined as follows. So this is our expected reward, or you can say return for the trajectory. This is our loss from the inverse dynamic model. And this is our loss from the forward dynamic model. So these losses are used and joint trained with the cumulative reward from one trajectory, and this overall loss is being minimized using the three neural networks that are parameterized by theta p, theta I, and theta f, where beta is a scalar that weights the inverse model loss against the forward model loss. And changing lambda is a scalar that weights the importance of policy gradient loss against the importance of learning intrinsic reward signals. So what is a policy gradient loss? The policy gradient loss helps in learning a policy using the parameterized loss or you can say the gradient of the uh, policy, which is pi SA. So coming to the experimental setup of the paper, they have used the environment named as Do My Home V0.
Shivanshu, maybe before coming to experiments, we can have a look at the model architecture,
Yeah, sure,
and
sure.
you can explain the whole pipeline in a very brief or very short manner, right?
Okay, okay. So looking at the architecture, how it works is that suppose we have a given state ST, we have a behavioral policy pi, and we take in action AT defined by that policy, like we have AT sampled from that policy pi. Now inputs are being these inputs are being transferred to the ICM model, which gives us our internal reward, or you can say intrinsic reward, in such a way that the ICM pipeline is described as follows. It takes the action AT, gives it to the forward model. Now forward model gives us the estimate for our next state in the feature space only. And given our ST, our current state, those features are being used to make uh, to map our original states to our feature space, and that feature representation of our current state is given to the forward model to estimate the feature vector of our next state. And for the inverse model, the feature representation for both the current state and the next state are given to the inverse model that will be given estimate for our current action. Now, these outputs from the inverse model and the forward model are used to generate an intrinsic reward RIT at the current time step t. So suppose, as the paper described, that environment doesn't have a very dense reward systems, or you can say the agent does not actually receive rewards for taking any action in the environment, but this ICM model facilitates the intrinsic reward signals for the agent to learn a better policy and converts to an optimal one. So this is how our intrinsic reward actually facilitates learning in optimal policy when an agent is deployed on the higher dimensional spaces like that. I hope you get the point. Any
Yeah.
questions regarding this?
So the whole thing is about learning a better state representation, right?
Not actually learning better representation, but yeah, you can say that, because it is done in a cumulative way, like how good an action is being predicted by another model, and how good the feature representation is learned by another model, and using that cumulatively, that is used to generate our intrinsic reward, or you can say synthetic reward for our agent.
At the end, it will utilize uh, the new state representation and old state representation to give you the reward, right?
Yeah, exactly, exactly. Because the
And
environment doesn't reward the agent for taking any action, so we create a synthetic one.
yeah, yeah, sure. And the inverse model will will be utilized to predict the next action.
The current action.
Right, right, right. The
So
current
our
action.
original action is AT, and A hat T is just an estimate for the that action that we'll be taking in this time step T. So how good or well the prediction of A hat T is, the agent will learn a better policy in such a way that it takes the future actions in a guided way.
Yeah, sure, sure, sure. So maybe we can have a look at forward model again, just for a brief, how
Yeah,
the new state representations are going to model for reward prediction.
yeah. So this is our forward model. So as it is stated that first submodule encodes the raw states into a feature space phi st, and the second module of that forward model takes the input of the feature encoding from the current state and the next state to predict our action AT. So our AT hat is a prediction for the current action that is being done by this function, and the prediction error is actually minimized to make that action better.
Sure, sure, cool. So, so yeah, this paper is really interesting because they are linking, or they are utilizing the state features at best, right?
Yeah, exactly.
Right, right. Instead of trying to modulate or trying to reconfigure some sort of reward model, they focused on utilizing the best information possible for a state to guide for a current action, right?
Yeah, exactly. Because like in RL, like it is doomed to be having a reward function synthetically. People are trying to synthetically map, or you can say generate a reward function for every environment, which cannot be generalized over any algorithm. So this actually deals with that problem.
Exactly, exactly. Right, right.
Uh, so
Let's move. Yeah, Akash.
can you explain? Like, I understand they in the section 2.1 at the end they mentioned the third point, things out of the agent's control but not affecting the agent, like moving leaves, etc.
Yeah.
Like, how did they identify these things? Like, in even in their conference video, I see they excluded those parts and focus only on the relevant like feature they have extracted.
Okay. So that is done. Okay. So that is done by a inverse model only, like how the feature representation, or you can say the feature representation of the current state from the visual input are being mapped in our feature space. So that is taken care by the feature encoder of the environmental states. So the forward model gets the input from the input as a feature encoding, but the forward model actually takes care for how many, or you can say how things actually affects the learning. Like it actually deals with the input noise, or you can say white noise, which is being incorporated in a feature space. So the forward model does that in a way that these features, like only the relevant features which are useful for the agent to learn in a better way, are encoded in that feature space. So any noise will be disregarded by the forward model while encoding the state functions.
Okay, sir.
So it is being taken care in that way.
By disregarded, you mean uh, disregarded from the loss function, or disregarded uh, at the encoding part, right? Like they are not even encoding the leaves, or they're encoding the leaves, but those that particular representation will give you high loss, and therefore it will not jump for that particular representation.
Uh, yeah, exactly. So the age, like the forward model takes care for the like suppose we have an occlusion in our visual space, and that actually diverges the agent learning in a uh, it diverges the agent to learn or reach our goal in a such a way that the policy stops learning, or you can say the learning process halts at a point. So it resets the environment and takes care of that in the next trajectory that will going to happen in fewer time steps. So that is taken care in that way. Like the feature encoding space will be aware for such irrelevant features, so it won't be able to encode such irrelevant features in the next time steps. Or you can say we have a we have a threshold for the time steps, like we can say 350 steps, or you can say 280 steps to reach our goal. And in the next epoch, the agent will able to recognize what are the relevant features that are useful for the learning process. So it will disregard the some of the relevant features in the next epoch. Like they have effect for the agent, but it will learn how to disregard that.
Right, right. I hope Akash you got the point, right?
Yes, sir.
Yeah, yeah. So the curiosity itself term, I don't think so that this should be called curiosity, right? Because curiosity is something, if agent wants to do something, then it will go. But what they are trying to do is, they are trying to basically reduce the search space in such a way that whatever search space is reduced, it was not relevant for the agent.
Yeah, exactly.
Exactly, exactly. Sure. Cool. So let's jump to the experimental setup.
Yeah. So the first environment that they have used is the Doom 3D navigation task using the environment Doom My Way Home V0, which is a part of OpenAI Gym. And in that environment, the map consists of 9 rooms, and the agent is tasked to reach some fixed goal location from its spawning location. Now, the agent is spawned randomly on some locations. The agent only provides a sparse terminal reward of +1 if it finds the west, or 0 otherwise. So, this is our sparse reward settings. What they have done is they have pre-trained the agent on a different map with different random textures, and each episode lasts for around 2100 time steps, and it approximately takes 350 steps for optimal policy to reach the west location from the farthest room in the map. Now the training maps looks like this. They have trained on this map, and the test scenario looks like this. So suppose the blue are the spawning location where the agent can spawn itself, and from there it has to reach the goal by learning an optimal policy. And the second environment is the game Super Mario Bros. They have also considered 4 levels of the game, pre-training on the first level and showing generalization on the subsequent levels. Now they have different setups for that. The action space in that Mario is, we have 12 different actions, and the Mario art, and for the experiments they are trained using curiosity signals only without any reward from the game. So they have explicitly set the extrinsic reward for that environment as 0. Now these are some training details, that how they encode the RGB inputs from the visual space. And in order to model temporal dependencies of the state representation, which is being concatenated with the current frame with 3 previous frames. So they have using 4 like they have used the convolutional network with 4 input frames for every layer. And they have used the A3C architecture where all the agents were trained asynchronously with 20 workers using the SGD. And they have used the Adam optimizers. Now how they have described the A3C architecture. The input space ST is passed through a sequence of 4 convolutional layers with 32 filters each. And the kernel size of 3 by 3, it's stride of 2 and padding 1. They have used a exponential linear unit that is used at each convolutional layer. So these are the experiment setup for the Mario game. Now the architecture for the ICM, the inverse model first maps the input state ST in a feature vector using a series of 4 convolutional layers. For the inverse model, the phi ST and the phi ST plus 1 are concatenated into a single feature vector and passed as inputs into a fully connected layer. How does a forward model work? The forward model is constructed by concatenating the phi ST and our original action AT, passing it to a sequence of 2 fully connected neural networks. And the hyperparameters are as follows. Now they have taken the baseline with the ICM model coupled with the A3C algorithm. So firstly, the vanilla A3C algorithm with greedy exploration, and second is the ICM pixels, which actually is a variant of ICM where the inverse model has the curiosity reward dependent only on the forward model loss in predicting the next observation in the pixel space. So they have only used the forward model, and in the absence of inverse model, as we have know that the original states are being mapped to a feature space by the inverse model. So in ICM pixel variant of this module, will have to make predictions on the high dimensional pixel spaces only. So they have done this in that way. These are the 3 settings where the environments are tweaked with such a way that they have different reward settings for every environment. Now what they have done is they have 3 broad settings that are being evaluated on the 2 of these games, VizDoom and Super Mario's. First is sparse extrinsic rewards on reaching a goal. And second one is the exploration with no extrinsic reward. So the agent actually tries to learn an optimal policy with 0 rewards from the environment. And second one is the generalization to the novel scenarios. So suppose we have a learned policy on level 1, and that learned policy is being deployed on the level 2 without any fine tuning or what. So they've checked the generalization of learned policy in unseen scenarios. Now they have done varying degree of reward sparsity. So they have done 3 setups where the reward signals are dense, where reward signals are sparse and very sparse. So setup for this is that the dense reward settings, the agent can spawn at random, but if spawned closer to the goal, they have denser rewards, so it can learn even from the epsilon greedy policy. So this is actually observed when the any variant of the ICM is being deployed with a setting where environment actually has a dense reward system. But in case of sparse or very sparse reward signals, a significantly longer trajectory is needed to be optimized in order to learn an optimal policy. So suppose we have 17 different spawn location in an environment, and agent unfortunately spawns to a very start of the environment, which is farther from the goal location. So the agent has to model a very longer trajectory in order to learn any policy to reach the goal. And that is being shown where settings are sparse and very sparse reward signal. And plots for these are as follows. The ACM I3C, which is actually the vanilla and taken as the baseline, works pretty well in the dense reward systems. And you can say the vanilla A3C actually is able to learn, but not in a very good way. And even the ICM pixel, or you can say ICM without the inverse model coupled with the A3C, is able to learn the optimal policy where the reward systems are dense in a very good way. Like they have the same convergence for the rewards. Now for the sparse reward settings, the A3Cs completely fail to learn any policy. But you can see the ICM A3C, which is with our inverse model, is able to minimize the regret by a very large margin. So the regret optimality for this baseline is very good, and the second one where the inverse model is absent in the ICM, the policy able to learn and converge to a better place, but in a longer time steps. So the policy learning starts like around 4 million time steps, where in the presence of inverse model, the learning starts from the around 2.5 million time steps only. And as shown in the very sparse settings, the A3C vanilla and the pixel model, where the inverse model is absent, completely fails to generalize or learn an optimal policy. But our ICM A3C able to learn policy and converge to a better reward. Now, what they have described is in a sparse reward case, the ICM pixel and ICM have very similar convergence because with a fixed spawning location of the agent. The ICM pixel encounters the same textures as the starting of each episode, which makes it learning pixel prediction model easier as the compared to a dense reward case. And finally, in a very sparse reward case, both the A3C and ICM pixels fail to generalize or fail to learn any policy, where our ICM achieves a perfect score of 66%. This actually indicates that ICM is a better suited than ICM pixels for harder goal directed exploration tasks. Now, checking the robustness of the uncontrolled dynamics, they have augmented the agent's observation with a fixed region of white noise, which made up of 40% of the image. And in the VizDoom 3D navigation task, ideally the agent should be unaffected by this noise, as the noise does not affect the agent in any way and is merely a nuisance. Now, looking at the figure 6, shows how the learning process works. There is a very large variance between the ICM pixel and the ICM vanilla learning curve. And this is because the sparse reward system described above is that the proposed ICM agent achieves a perfect score, but the ICM pixel suffers significantly despite having succeeded at the sparse reward, when the inputs were not augmented with any noise. So this indicates that in contrast to the ICM pixel, ICM is insensitive to the nuances changes in the environment. So suppose we have the agent deployed in the level 1 of the Mario Kart game, and we are trying to generalize it to the level 2, but the agent fails to do so, and after some fine tuning of the policy, the level 2 is learned the level 2 is achieved with a learned policy, but that generalization doesn't help to learn our level 3. So that is discussed in the next part. Now they have compared it to a TRPO, which is the trust region policy optimization, which is actually more sample efficient than A3C, but it takes a very long time to learn too. So they haven't shown the part, but the results are on the table. And what they have done is when no reward signal, so there are the extrinsic reward from the environment and the ICM is set to 0. They have evaluated the what portion of the map was explored in that VizDoom environment and how much progress it made in this setting. So results are as follows. Now talking about the generalization to a novel scenario, the It is however, it is remain unclear whether the agent has done this learning as a generalized skill for effectively exploring its environment, or it is simply memorizing the training set. So they have tested it, like how much the learned behavior is specific to the particular space and how much is general enough to be useful in a novel scenario. So what they have done is using a setting named as the as it is, using the policy as it is and changing the environments. So they have observed that the policy from learned on the level 1 and level 3, they have similar visual appearances, but the level 2 is actually needed to be fine tuned for the environmental changes that are being incorporated, as the level 2 is being labeled as a dark world, or you can say a night world, by while the level 1 and level 3 has the same daytime appearances. So they have changed the setting, and they have fine tuned the curiosity model in such a way that policy learned from the level 1 is fine tuned to work on level 2, which quickly overcomes the mismatch in the global visual appearances and achieves a higher score than the training from scratch. So, if you deploy a training policy on level 2 from scratch, that is being defeated by the level 1 policy, which is fine tuned for that level 2. And they have described that training from scratch on level 2 is actually worse than the fine-tuned policy, even when they're training for more iterations than pre-training. So they have shown that the level 2 is more difficult than level 1. So learning the basic skills such as moving, jumping, killing enemies from the scratch is much more dangerous than the relative safety of level 1. These are the results that they have concluded. Now, the interesting point is that the fine tuning of the exploration policy that was pre trained on level 1 to level 3 deteriorates the performance compared to the as it is running. This is suppose we have a policy learned on level 1 and that is being fine tuned for level 2, and then we use that policy uh, to learn for the level 3. So what they have concluded that fine tuning the level 1 policy for the level 3, like we have similar visual appearances for level 1 and level 3, that policy is actually responsible for zero curiosity models to the agent. So it actually creates a bottleneck, or you can say curiosity blockade, and is unable to make any progress. This is because the level 3 is very hard for the agent to cross beyond a certain point, because it receives almost no curiosity reward, and as a result its attempt to update its policy with almost zero intrinsic rewards, and the policy slowly degenerates. So this behavior is actually vague, analogous to the boredom, or you can say how a human learns, where the agent is unable to make any progress and stop exploring, because the learned policy from level 1 was being fine tuned for the level 3. So policy was so good that agent doesn't actually receive any reward for that. And repeating that only, generalizing and fine tuning the ICM A3C from level 1 to level 2 results in a significant leap. And when the level 1 learned policy is fine tuned for level 3, the results are catastrophic outcome. So, as we have discussed, that level 3 is a very hard stage, but visual appearances are very similar. The fine tuned agent fails to generate any curiosity for the learning process. So, agent tries to perform updates with no, or you can say zero intrinsic reward or curiosity. So, this is how we have summed up the paper. Any questions regarding this? Yes, Siddhant.
Right. So, not that particular not like a question on the model architecture, but why is agent not able to perform when the level 1 and level 3 are of similar appearances, and on level 1 it is performing good, but fine tuned for level 3 it is not performing really good.
Yeah, so I got your point. Like it is actually a vague observation. Like they were shocked for how the fine tuning works. So let us assume that we have three levels: level two, level and level three. So a policy pi is being learned on level one, and they have tested the generalization for that policy on level two. Suppose we have pi one on that only. Now they have seen that the visual appearances for level 1 and level 3 are the same. Like suppose they both are the daytime environments, and the level 2 is nighttime environment. So the generalization fails for the level 2. So they have to fine tune the policy learned from the level 1 to make it a better policy for the level 2. But when they have done fine tuning on the level 1 policy for the level 3, they have concluded, or you can say they have observed, that the policy is so good for the environment. Like they have same appearances and the agent have learned from the past experiences. The policy makes the agent to not to explore in the level 3. So the performance actually degrades because the policy has fine tuned in such a way that RTI, which is the intrinsic reward, actually tends to be zero. Like there is no curiosity for the agent to learn from. And the settings is obviously we have sparse reward systems. So there is actually no extrinsic reward from our environment, and supposedly we have zero intrinsic reward for the agent while we are using the fine-tuned policy for level 3. So the agent fails to learn anything, or you can say that policy even degrades, or you can say degenerates to perform well in the level 3.
Right, so curiosity is zero, that is why it is not exploring the level 3, and without exploration it is
Yeah, because the
losing.
rewards are zero, and but every step the agent has to update its policy. So the policy updates are being sorry, the policy updates are being zero completely. So policy doesn't improve, but actually degrades with time.
Sure, sure, sure. Cool, cool, cool. So yeah, looking at the time, we have exceeded our limit, and uh, we can we always can do more discussions in our Slack group. So right. So yeah, it was a great discussion, and thank you, Shubhanshu, for
Thank you.
presenting this really interesting paper. And we will see how this ICM concept moves around in our RL space. Right.
Yeah, we
Cool,
will.
everybody. Have a
Yeah,
nice day. And Akash, if you have any doubt, you can ping us in our Slack group
Okay, sir.
and discuss further. Right. Thank you. Thank you, everybody.
thank you.